Hey guys, welcome to video 43. Today we're going to take a look at the JFET used as a small signal amplifier. On the left hand side of the screen we've got an N-channel JFET biased up using source feedback biasing, and once we've established a cue point we're going to use this small signal model to represent the JFET. This is a voltage controlled current source. The gate to source voltage controls the drain current, and the gain parameter that relates these two quantities is little g sub m, the transconductance of the FET. Now, looking into the gate terminal, we're going to see a resistance little r sub gs, and because this is essentially a reverse biased PN junction, RGS is going to be extremely large, typically on the order of 100 megohms or more. So we're usually just going to consider this to be infinite. And similarly, R sub O, the internal resistance of this current source, is usually very large compared to the external circuit resistances. So we're going to consider that to be infinite most of the time as well. And when we do this, we can use this simplified small signal model over here. Now, the overall general characteristics of the JFET are: it's a voltage-controlled current source, or sometimes called a VCIS, or transconductance device, or transconductance amplifier. GM, transconductance, is the gain parameter of the JFET. At relatively low frequencies, that is audio frequencies, we're going to assume RGS is infinite, and in most applications, little r sub O is large enough to consider to be infinite as well. Now, what I'd like to do next is take a look at the data sheet for the MPF 102, which we've talked about many times before. And what I want to do in particular is talk about the transconductance, what we're calling little g sub m. Okay guys, so here is the data sheet for the MPF 102, and what I want to look at on here is down under small signal characteristics, the forward transfer admittance, that's little y sub fs, and we've got the absolute magnitude here as well, and I'll explain that in a second. But this is equivalent to GM, the transconductance of the FET that we've been talking about. They're using y, which is a complex number. It's the reciprocal of z, and the reason for that is because the MPF 102 is designed to be used at very high frequencies, the hundreds of megahertz, and at those frequencies almost all the parameters for the JFET are going to be complex numbers. We're not working with frequencies like that. We're down in the audio range, so we're dealing with real valued parameters. All right, and so if we look at YFS, that is transconductance, at low frequencies, 1 kilohertz, as we have listed here, it has a minimum value of 2,000 micromhs and a max of 7,500 micromhs. Now, remember, mhs is the reciprocal of resistance, and Y is the reciprocal of Z, just like G is the reciprocal of R. So we're going to be dealing with a lot of parameters and their reciprocals, and it takes a little getting used to. But one of the things you'll find out eventually is that FETs have a lot in common with vacuum tubes, and we're going to see a lot of this terminology used there in the future as well. But anyway, I wanted to use this as a segue to introduce the notation here, and that is we're going to measure or specify transconductance in the units of mhs, which is represented with an upside down omega. The SI unit for conductance is the Siemens, capital S, but a lot of times when I write that it looks like a 5 or a lowercase s. It's very confusing. I like the upside down omega. So when I talk about conductance or transconductance, I'm going to use mhs, which is represented with the upside down omega. All right, so with that in mind, let's move to the next screen. Okay, here we're going to talk a little bit more about transconductance. If we establish a cue point somewhere on the curve, say right here, the transconductance of the JFET at that cue point is the slope of the tangent line at that operating point. So if I sketch the slope of this tangent here, it looks something like this, let's say. If I measure the slope of this line, that is GM at that cue point. Now, if I were biased up, say, at this point on the transconductance curve, the tangent line would look something like this. We've got a lower slope, so the transconductance is smaller at this Q point versus this one. And if I were to establish my Q point all the way up here at IDSS, I'd get the steepest slope of my tangent here, something like this. And that would be the maximum transconductance that I could get. Of course, I'm already at the limits of operation, so it's not a practical Q point location, but you get the idea. The transconductance is dependent on where our Q point is located. Now, technically, transconductance is the derivative of drain current with respect to VGS. And I'm not going to put you through all the calculus and stuff at this point. I'm going to save that for the end of the video, so you can skip it if you want to. And I'm just going to show you the end results. The maximum transconductance that occurs at this point is called GM0, and we usually just call that GMO, and it's equal to 2 IDSS over VP. All right, that is the maximum possible transconductance, at least in this operating region. The operating point transconductance, just labeled GM, is given by GMO times 1 minus the magnitude of VGS over VP. And I'm using the magnitude and VP because these are positive numbers, and you're less likely to make mistakes entering these in your calculator. So rather than using VGS off and VGS, I'm using the magnitude of VGS and VP. All right, and again, the units of transconductance in SI units, it's the Siemens S, but we're going to use mhos, which is the upside down omega. Now, there are 3 basic amplifier configurations that are analogous to the same ones we had for the bipolar transistor. Starting with the most commonly encountered, we've got the common source configuration, and this is equivalent to the common emitter. It's got inverting gain. The voltage gain is typically much greater than 1. It's got very high current gain, very high input resistance. The output resistance is medium or moderate, similar to what we have for BJTs. And it's got the highest power gain of all 3 configurations. The source follower, or common drain, which is equivalent to the emitter follower, has a voltage gain less than 1, but it has very high current gain, very high input resistance, and its output resistance is low, at least compared to the common source and the common gate, which we'll talk about next. This is equivalent to the common base amplifier. It's going to have the best frequency response of all of these circuits. Its voltage gain is greater than 1, but its current gain is less than 1. The input resistance is low, and the output resistance is moderate or medium. All right, and these are all essentially analogous to the BJT equivalents. Now let's go take a look at a common source amplifier. On the left-hand side of the screen, we've got an N-channel JFET biased up using source feedback biasing, and we've capacitively coupled the input source to the gate, capacitively coupled the load resistor to the drain, and I've used a source bypass cap across RS as well to maximize voltage gain, just like we would in a common emitter amplifier. The AC equivalent circuit is shown over here. It's pretty straightforward. R prime D is the parallel combination of RD and RL. And notice, because the drain current flows counterclockwise around this loop, that V out is negative when V in is positive going, so we do get inverting gain as we saw earlier. Now, the voltage gain of this amplifier is equal to negative GM times R prime D. That is the transconductance times the equivalent drain resistance. And the input resistance is approximately equal to RG, because remember, we've got a reverse biased PN junction here. It's got virtually infinite resistance, so all the source sees is RG. Now, we have to have a resistor here because there has to be a path for leakage current to flow out the gate to ground. But because it's so small, we can make RG very large, typically 1 megohm or even larger. Now, something I'd like to mention before we move on is that even though I've bypassed the source to ground, notice that the input resistance is still practically infinite looking into the JFET. bypassing the source resistor does not affect the input resistance like bypassing the emitter resistance does in a BJT amplifier. If we had done this to a BJT amp looking into the base, we'd probably only see maybe a couple of hundred ohms. In this case, bypassing the source doesn't really have any detrimental effect on input resistance, so we might as well just always bypass the source to maximize voltage gain, because as we'll find out soon enough, JFETs are not really great in terms of voltage gain anyway. All right, let's put all this newfound information to use by working a couple problems. This first example, we've got an MPF 102 with the typical parameters I derived a few videos ago. It's a common source amplifier, source is fully bypassed, and we're using source feedback biasing. Let's start by determining GMO, and we know GMO equals 2 IDSS over VP. So let's call up our calculator. IDSS is 6 milliamps, so that's 0.012 divided by 2.5 volts is 4.8 millimos. Okay, so GMO is 4.8 millimos. We could call that 4,800 micromos if we wanted, but I'll stick with milli. The next thing we want to do is determine IDQ, and I'm going to use the online equation graph or Desmos again. I've already got my transconductance curve on here, so all I need to do is enter my negative ID times RS line. And on here we enter that as negative X divided by RS, which was 100 ohms. And here is our resulting plot, and the intersection here is 4.2 milliamps, let's call it. Okay, so we're going to have an IDQ of 4.2 milliamps. VDSQ equals VDD minus IDQ times RD plus RS, and let's see what that gives us. Let's see, RD plus RS is 1100 times 4.2 milliamps, 0.0042, and we'll subtract that from VDD, which is 12, and we've got a VDSQ of about 7.4 volts. All right, our transconductance at the Q point, GM, is equal to GMO times 1 minus the magnitude of VGS over VP. And if we call up the calculator, let's see what we get here. VGS is IDQ times RS, so 4.2 milliamps times 100 ohms is 0.42 volts divided by VP, which was 2.5. We'll subtract that from 1 and multiply that times IDSS, or I'm sorry, times GMO, so times 4.8 is, let's just call that 4 millimos, okay? So GM is 4 millimos. Right, now we can find our voltage gain. Well, almost. We need to find R prime D first, so let's do that. R prime D equals RD in parallel with RL. So we've got 1K in parallel with 1.5K. I know that one, that's 600 ohms. All right, so our R prime D value is 600 ohms, and our voltage gain then is negative GM times R prime D. So that's 4 milli times 600, and let's enter that 0.004 times 600 is negative 2.4. Wow. Not much voltage gain, but as I said earlier, JFETs are not known for their high voltage gain, and in this case we see why. We've got a fully bypassed source, and we only get a voltage gain of negative 2.4. If we had a fully bypassed emitter on a common emitter amplifier like this, we'd probably have a gain well over 100. So, you know, if you're looking for voltage gain, JFETs are not the device to use. All right, let's see. Our input resistance, that's going to be approximately RG, which is 1 megohm. And now let's find our current gain. Let me clear out a little space here. And if you recall, A sub I is equal to AV times Rin divided by RL. So let's see what we come up with here. Okay, calling up the calculator. Rin is 1 meg divided by RL is 1500 times the voltage gain, which is 2.4. So current gain is 1,600, actually negative 1,600. So it's pretty respectable. Negative 1,600. That's where the JFET shines. It's got very high current gain. The only way we could do this using BJTs is probably with a Darlington or a Z-Cli pair. So these are the good things about JFET amplifiers: the high input resistance, high current gain, and let's see what our power gain is. A sub P equals AV times AI, and so we've got 1,600 times 2.4, which gives us a power gain of 3,840. Okay, 3,840. Not too bad. All right, so there we go. There's our first analysis of a JFET small signal amplifier. Not much in the way of voltage gain, but current gain and power gain are pretty decent. Let's do another example. All right, this circuit has a JFET with an IDSS of 10 milliamps. VGS off is negative 3 volts, VP is 3 volts. And it's, again, a common source amplifier, fully bypassed using source feedback biasing. The first thing we're going to do is find GMO, and GMO equals 2 IDSS over VP, and 2 IDSS is 0.02 divided by 3 gives us a GMO of about 6.7 millimos. 6.7 millimos. All right, we'll find IDQ using the online graphics calculator again. We're going to have to change our device parameters. Our IDSS is now 10 milliamps, and VP or VGS off is 3. And there's our new transconductance curve. Our ID times RS biasing line is again going to be negative X divided by RS, which is 100 ohms again. So there are our curves, or our graphs of our equations, and our solution gives us an IDQ of about 6.3 milliamps. Okay, so IDQ is 6.3 milliamps. VDSQ equals VDD minus IDQ times RD plus RS again. So what do we get here? Let's see. RD plus RS is 1,300 times IDQ is 6.3 mils. Subtract that from a VDD of 15 volts, and we've got a VDS of about 6.8 volts. 6.8 volts. Our transconductance, GM equals GMO times 1 minus the magnitude of VGS over VP. Let's see what we've got here. Let's see. VGS is going to be ID times RS, 6.3 mils times 100 is 0.63 volts divided by 3 volts. Subtract that from 1, and we multiply times GMO is 6.7 milli, and that gives us a GM of about, let's call it 5.3 millimos. 5.3 millimos. All right, now R prime D is again RD in parallel with RL. So let's see what we get here. RD is 1200. Whoops, that's 1200 in parallel with 2000, and that gives us 750 ohms. All right, so we got 750 ohms, and our voltage gain equals negative GM times R prime D. So that's going to be 750 ohms times 0.0053 is a voltage gain of pretty darn close to 4, and it's actually -4, so it's a little better than it was for the previous amp, but nothing great. And again, that's what we expect with JFETs. They're just not very high voltage gain devices. All right, our input resistance is RG, that's 1 megohm. And our current gain then is AI equals AV times Rin over RL. Rn is 1,000,000 divided by 2K is 500 times -4, so we got a current gain of -2,000, and our power gain is 2,000 times 4, which is 8,000. So there's another analysis example. We got a little better voltage gain this time, but again, nothing too impressive, but that's to be expected. All right, let's do one final example here. All right, this time we're going to do a little bit of design. What we've got is an MPF 102 used as a little variable level booster or preamp or overdrive. We've got a 9-volt battery for power with a 1/4-inch stereo jack used for power switching, and we've got a 500K potentiometer to adjust the level of this amplifier. And what we want to do is choose R2, the drain resistor, and R3, the source resistor, to give us an IDQ of approximately IDSS over 2 and a VDSQ of around 4 volts. All right, so what we're going to do to start is come over to our transconductance curves and locate our Q point drain current, which is 3 milliamps IDSS over 2. And there's our Q point. And if we come down for there, we're over 3 divisions to the left. So that's 3 times 0.25, which is -0.75 volts. So that's our desired VGSQ, -0.75 volts. We're going to find the value of the source resistor R3 using Ohm's law. R3 is equal to 0.75 volts divided by the current flow, which is 3 milliamps. And let's see what that gives us. 0.75 divided by 0.003 is 250 ohms. Okay, so we need a 250 ohm resistor for R3. Now that's not a standard value. We could use the next lower value, which is 220, or the next higher value, 270. I'm going to go with 270 ohms. It's a little closer to this, and it'll give us a little less than 3 milliamps, but probably not much. So let's go with 270 ohms for R3. And now let's calculate the approximate voltage drop we'd have down here. That's going to be 270 ohms times 3 milliamps is about 0.8 volts. Okay, so we're dropping about 0.8 volts here. We want to drop 4 volts here, so that leaves us, let's see, 9 minus 4 minus 0.8, 4.2 volts across R2. Okay, 4.2 volts. So we're going to use Ohm's law again. R2 equals 4.2 volts divided by the drain current, 3 milliamps. And what do we get here? 4.2 divided by 0.003 is 1.4 k ohms. 1.4 k ohms. Again, not a standard value, but the closest standard value is not too far off. That's 1.5 k ohms. And since our drain current's a little bit less than 3 milliamps, that might work out pretty well. Okay, so this is our design. Let's see how close it comes to our requested values. All right, so let's go back to Desmos and we'll find IDQ for this thing. Let's see, we've got to change the parameters to match the MPF 102, so that's 6 milliamps for IDSS and -2.5 volts for VP or VGS off, and our ID times RS load line is going to be -X divided by, what was our value? 270 ohms. Okay, so 270. And there is our solution. We've got a drain current of about 2.86, let's call that 2.9 milliamps, okay? Not too far off. We're actually running at 2.9 milliamps. Our VDSQ is going to be very close to 4, but let's see what we get here. VDSQ equals VDD minus IDQ times RD plus RS. And let's see what we've got here. Let's see. Let's clear this. We've got 1500 plus 270 times what was our current, 0.0029, and we're going to subtract that from 9, which gives us about, let's call it 3.9 volts. That's pretty darn close to our desired 4 volts, okay? 3.9 volts. Our transconductance at the Q point, let me clear off a little room here to work, and let's see what our transconductance is. GM equals GMO times 1 minus VGS magnitude over VP. So what do we get here? Let's see, clear. VGS is 0.8 divided by VGS off, or VP, 2.5 minus 1 times our GMO was 4.8. So we've got a GM of, let's call it 3.3 millimos. 3.3 millimos. And since we don't have an external load on this circuit, the R prime D is just 1500 ohms. So AV equals negative GM times RD for this circuit. So we've got a GM of 0.0033 times our drain resistor was what, 1.5K, 1500. So we've got a gain of almost 5 in this case. That's a little better than we've had before. So our overall gain is -5. Now remember, when we connect a load here, it's probably going to reduce the gain somewhat, but if it's a high impedance device we're driving, our gain will still stay pretty close to -5. All right, so here we have a nice little booster, and it's an example of a design problem. So that finishes up the examples for this video. What I want to do next is derive the transconductance equation for this. So those of you that aren't interested in the math, you can go ahead and leave, and I'll see you the next time. For those of you that are curious, we're going to dive into that for a few minutes. All right, now rather than write it out longhand like I've done before, I just decided that I would do it nice and neat, typeset, and just walk you through the steps in every detail. A lot of times when guys derive equations in books and so on, they leave out lots of steps, but not everybody's good at algebra or calculus. So I like to include all the details, and that's what we're going to get here. So let's start. We have transconductance is the derivative of ID with respect to VGS, and then we substitute in our equation for drain current, and we're going to expand this factor in parentheses using the FOIL method, which gives us the derivative of these three terms: IDSS, 2IDSS over VGS off times VGS to the first power, plus IDSS over VGS off squared times VGS squared. All right, we're going to take the derivatives term by term. So we've got the derivative of IDSS, the derivative of negative 2IDSS over VGS off times VGS, and the derivative of this squared term, okay? Now, I'm going to bring the constant factors outside of the derivatives just to make things clear, okay? So there is no factor here other than IDSS, and the derivative of a constant is 0. In the second case, I brought out 2IDSS over VGS off, and now we're taking the derivative of VGS with respect to itself, and that's equal to 1. Then finally, we've got IDSS over VGS off squared times the derivative of VGS squared with respect to VGS, and that has a value of 2 VGS. So our derivatives for the first term are 0, the second term 1, and the derivative here is 2 VGS multiplied by the coefficients. So the resulting expression we have is shown here, and we can factor negative 2 IDSS over VGS off out of both of these terms, and that leaves us with this expression number 7. Okay, there's a lot of negative signs in there, and VGS off is a negative value. I don't like doing calculations with lots of negative signs, so what I'm going to do is replace negative VGS off with VP and the magnitude of VGS rather than its negative value, and that gives me this easier expression to work with. Okay, and since we know that 2 IDSS over VP is GMO, we can make things a little prettier by making that substitution, and then we end up with the equation that's in most of the textbooks, that is transconductance GM equals GMO times 1 minus the magnitude of VGS over VP. All right, and I hope that was at least a little bit helpful to you. And if you're just starting out learning calculus, this is a pretty nice little practical example of where derivatives are used. All right, so that ends today's video. I hope it wasn't too painful, and I'll see you guys the next time around.